You probably don't think much about the strength of the soil beneath your feet, but some of us have dirtier minds than others. Just about every structure out there sits on the ground, and anyone who's ever built a sandcastle knows that soil's not all that strong. So if we want our buildings and bridges and pipelines and roads and anything else that sits on the ground to keep standing, and especially if we want to use the earth itself as a construction material, we're going to need some geotechnical engineering. Soils are frictional materials. Rather than being held together by molecular bonding like steel or by a binder like cement and concrete, their strength almost completely depends on internal friction between the soil particles themselves. Pour out some sand on a table and you'll notice that the pile forms a slope. The angle of this slope is called the angle of repose, which is the steepest angle at which a soil can naturally rest. In other words, this is the slope at which the shear stresses within the soil, due to its own weight, are exactly equal to the shear strength caused by the internal friction. Any steeper and the soil will slide. Let's look back at our sample of soil. If we put the sample back into the ground, now it's surrounded by additional soil that can apply horizontal pressure. This is called confining pressure, and it helps balance out vertical forces like the weight of the soil itself. This confining pressure is the reason that a granular material can be stable at a slope, but usually won't be stable vertically. This can be a problem if you're trying to build an earthen structure for two reasons. First, it takes about twice as much material than if you're using something that can stand vertically. And second is space. In crowded cities, space is at a premium. If you're building an earthen structure, every foot that you go up in height, you have to go that far out as well, or even further. So what's a geotechnical engineer to do? What if there was a way to add confining pressure to the soil without having to build on a slope? Behold, reinforced earth. Just like rebar and concrete, you can create an incredibly strong composite material with soil just by adding reinforcing elements.
Through the years, using straw, sticks, and branches to reinforce adobe bricks and mud dwellings has happened since the earliest part of human history. And in the 1970s, French architect and engineer Sir Henry Vidal invented the modern form of earth reinforcement techniques. He termed terre armée or reinforced earth. These techniques involve the incorporation of tensile elements into a soil mass to complement the soil's compressive strength and to improve the mechanical properties of the soil mass. Reinforced earth is based on a simple concept. As originally conceived by its inventor, the interplacing of soil and reinforcements develops friction at the points of contact between the two, resulting in a permanent and predictable bond and creating a unique composite construction material. Reinforced earth structures combine select granular, engineered backfill with steel or geosynthetic tensile reinforcements and a modular facing system, generally made of precast concrete panels, welded wire mesh, or semi-elliptical steel panels. This unrivaled combination creates a durable, mass gravity retaining structure which, in addition to its own weight, is able to support large dead and live loads imposed by associated structures and vehicles. By 1967, several major reinforced earth structures had been constructed in Europe, and by the early 1970s, this versatile and dramatically cost-effective technology was in use in more than 30 countries throughout the world. Invited by the Federal Highway Administration in 1971, Vidal brought his technology to the United States to solve a difficult landslide problem near Los Angeles. Following the successful project, and with the encouragement of financial support from an FHWA demonstration project, additional reinforced earth structures were soon constructed in Washington, Tennessee, Georgia, Nevada, Pennsylvania, and Minnesota. These projects were technically challenging, including landslide buttresses in mountainous areas, bridge abutments, high retaining walls, a wall along a tidal estuary, and even a foundation reinforcement slab over a sinkhole-prone area. From these first experiences, it was recognized that this material, with its unique high strength and flexibility, could be constructed under both ordinary and adverse conditions and would support extremely heavy loads, even on marginal foundation conditions. This and other reinforced earth systems have become known as mechanically stabilized earth, or MSE, and their use has significantly increased. The primary types of MSE systems which have emerged include reinforced embankments over soft foundations, or RESF, reinforced soil slopes, or RSS, and mechanically stabilized earth walls, or MSEW. MSEW and RSS have become especially important in highway construction, as their use reduces the required width of new right-of-way and facilitates construction within existing limited right-of-way. On the other hand, RESF are recognized as a cost-effective alternative to traditional techniques for constructing earthen embankments over low-strength foundations. Now let's talk about the MSE walls, or the mechanically stabilized earth walls. MSE walls stabilize unstable slopes and retain the soil on steep slopes and under crest loads. The wall face is often of precast, segmental blocks, panels, or geocells that can tolerate some differential movement. The walls are infilled with granular soil, with or without reinforcement, while retaining the backfill soil. Reinforced walls utilize horizontal layers typically of geogrids. The reinforced soil mass, along with the facing, forms the wall. In many types of MSE, each vertical fascia row is inset, thereby providing individual cells that can be infilled with topsoil and planted with vegetation to create a green wall. The selection of mechanically stabilized earth walls will vary from one site to another but can be used in these situations as temporary structures for highway projects, used as soil retention structures or dikes, as containment structures around oil tanks, containment structures around gas storage tanks, dams constructions and levees additional height increase capacity. For creating storage areas. At construction sites with poor soil conditions. On areas of high seismic activity. Bridge abutments. On wing walls. Contractors and builders tend to choose MSE wall system due to its great economic and constructive benefits. Here are some of the reasons. Simple construction. The use of heavy equipment is reduced. More land is available for construction. Faster construction than traditional concrete walls. Do not require specialized labor. Reduces the need for wall finishing. Less site preparation is needed. Can be built in confined areas or areas where a concrete wall is almost impossible to be constructed. Reduces the need for land acquisition process. Mechanically stabilized earth walls are susceptible to elastic deformation. High seismic load resistance. MSE walls can be used as tall structure exceeding more than 60 feet of wall height. Can be combined with other products. Various shapes and forms can be made. Excavation works for footings are reduced. And lastly, can be built in poor soil areas. The engineer's ability to increase usable property economically has become an important factor in all segments of property development. Increasingly, residential, commercial, and industrial developers, as well as transportation and infrastructure facility designers, are faced with the challenge of maximizing land use in areas that often have both difficult topographic characteristics as well as difficult soil conditions. RSS, or Reinforced Steep and Slope System, provide a cost-effective means to achieve more efficient grade changes compared with the conventional unreinforced slopes. Reinforced steeping slopes are soil structures constructed with a slope face angle up to as high as 80 degrees from the horizontal. Typical unreinforced soil slopes are limited to a slope face angle of approximately 30 degrees or less, depending on the angle of repose of the slope zone. Here are some of the reasons why RSS system is beneficial to some construction areas. First, it can be used in slopes that are common geographic features and can be found everywhere, with steepness ranging from gentle swales to ultra-steep mountain sides. Second, it provides transportation right-of-ways and building sites. Third, can be associated with a particular highway alignment. Development of a parcel of land may be determined by the ability to create sufficient, flat, or level land to satisfy space, safety, or access requirements. Historically, construction of embankments is costly and environmentally sensitive when very soft soils, especially in wetlands, are encountered. The primary problem with these soft soils results from their low shear strength and excessive consolidation settlements, requiring special construction practices and leading to high construction costs. There are typical solutions available to reduce the problems associated with soft foundations. These solutions include: first, removal and replacement of soil. Second, displacement of compressible material by end loading. Third, stage construction, placing fill at controlled rates to allow for consolidation and strength gains. Fourth, installation of drains to facilitate consolidation. Fifth, preloading the site to reduce settlements of the structure and provide higher strength. Sixth, soft soil modification using admixtures, for example, soil, cement, lime, or injection. Seventh, reinforcement of the soil matrix using a structural element. There are also geotechnical solutions to address the problem with soft foundations. In order to minimize the potential of sudden settlements, which would be a danger for the public traffic, modern preventive measures using high-strength geosynthetics are recommended. In the case of a sudden damage of the subsurface, the geosynthetic acts as a membrane keeping the road or railway structure intact until further repair measures can be undertaken.